In Module 7, we are going to look at confidence intervals for one population mean. So we were looking at descriptive statistics up until this point, and now we're going to look at inferential statistics where we make an inference, and in this case, we're going to make an inference by examining methods for estimating the mean of a population. In the previous module, we did look at how mu is roughly equal to the sample mean, but there will be sampling error, and so we need to get accuracy around our estimate, and that's what we'll be talking about today. I want to introduce this topic with kind of an example. So I've been watching the Olympics, and I don't know if you guys are into the Winter Olympics, but I suddenly become a world-class athlete, knowledgeable on all things sports when the Olympics comes on. But I was watching curling with my husband, and so you can see that we had from Czechia, there's this guy here, Lukas Kilma, and he's on the Czechia curling team. And my husband said, "Oh my God, he's got such big arms." And I looked at him and I thought, like, I don't know, does he have big arms? And then you can look at the Canadian, Mark Kennedy, and when you look at his arms, you're like, okay, yeah, this guy does have big arms. But I also have here that this guy has a big mouth, because I don't know about you guys, he was busted cheating and he was swearing, which I didn't think was very Canadian of him. So how does this play into confidence intervals? Well, I'll tell you exactly the thing. I don't understand when somebody, like a man, has big arms compared to small arms. I need to know the lowest kind of point at which your arms are considered, and then the highest point at which your arms are considered. So if you look at, say, all of the men on the curling teams and you wanted to figure out their average arm size, you know that there's going to be error in that. So there's going to be a lower end and a higher end, and then there will be a mean somewhere in there. And that's what confidence intervals are. They're just the bookends for where your mean is going to fall. And then, of course, you always attach it to a confidence estimate, so 95% or 99%, so that you can say, hey, I'm 95% confident. The mean's going to fall in between, Mark Kennedy and Lukas Kilma, somewhere in between those, where, say, this is the lower bookend and this is the higher bookend. That's what confidence intervals are. So one of the biggest problems we're always going to have in statistics is that we can't get information about the whole population. It's really, really difficult. So if the population is small, you can usually figure out mu by taking a census and then computing basically the population mean. But if the population is large, it's really, really hard to do the census. It's really impractical. And you might want to estimate a population mean for a bunch of different reasons, like things like the mean age of people working in a hospital, or the mean cost of a wedding, or the mean gas mileage of different types of ambulances, or the mean starting salary for nursing graduates. But it's really difficult to do that, and so that's why we do a point estimate. And a point estimate is one way we can obtain information about the population mean without totally taking a census. So one way to get that information without estimating the population mean with a census is just to take the sample mean, and we call this a point estimate. So you can see in this example here, we've got the prices of 36 randomly selected new mobile homes, and we're just showing you here that X bar is equal to the sum of X over N, which we already know, but this is, roughly speaking, a point estimate of our parameter, and it's our best guess for the value of the unknown parameter based on sample data. This is our official definition for the point estimate. A point estimate of a parameter is the value of a statistic used to estimate that parameter. So for instance, a sample mean is a point estimate of a population mean, just like a sample standard deviation is a point estimate of a population standard deviation. So we can talk about unbiased versus biased estimators as well. So generally, a statistic is an unbiased estimator of a parameter parameter if the mean of all its possible values equals the parameter. Otherwise, the statistic is called a biased estimator of the parameter. So we want our statistic to be unbiased and have a small standard of error or standard error. In that case, chances then are good that our point estimate, or the value of the statistic, will be close to that parameter. So the sample mean is usually not equal to the population mean. There's going to be some sampling error. And because there is sampling error, we always want to accompany any point estimate of mu with information that indicates the accuracy of that estimate. And this information is called a confidence interval estimate for mu. And I've got pictures of books on here because, again, go back to the curling example. We're looking for those bookends that would go around our estimate of mu. So let's do an example of this. Now, this is just introducing the confidence intervals, and so keep in mind that we aren't always going to be able to use the empirical rule, and that will make more sense as we go through. So let's do this example. So this is the prices of new mobile homes. So again, consider the problem of estimating the population mean price mu of all mobile homes by using the sample data that we looked at before. Let's assume the population standard deviation of all such prices is 7.2 thousand. That's 7,200. And what I always do is when I'm working on these questions, now that I know that, I will pull off to the side and I'll put down the standard deviation, or sigma, is equal to 7,200, and then I just have that information. So we might know the population standard deviation from previous research or from a preliminary study of prices. Often we don't actually have that number, but we'll get there when we get there. Okay, so in this example, A, identify the distribution of the variable x bar, that is the sampling distribution of the sample mean for samples of size 36. Use part A to show that approximately 95% of all samples of 36 new mobile homes have that property that the interval from x bar minus 2.4 to x bar plus 2.4 contains mu, and then use that and the sample data to find a 95% confidence interval for mu, and that is an interval of numbers that we can be 95% confident contain mu. So we'll go through each one of these step by step. So the first part of this question in A was asking us to identify the distribution of the variable x bar. And so what they're trying to do, or what they're trying to get you to do essentially, is to determine, first of all, is this a normal distribution? Is this data normal? So you would have a list of data, you would have a chart or a table, and what you could do is you could run a normal probability plot shown here, and you can see if it's generally linear, then you can say that it is normal, or of course you could run a Shapiro-Wilk. The other part of this is that they want you to write out what you know, essentially. So we know n is equal to 36, they told us, and we know that the standard deviation is 7.2 or 7,200. Okay, so now they're asking in the next kind of part of that to identify the sampling distribution. So we can lean into the module that we did prior to this, where mu x bar is equal to mu. Now we don't actually know what mu is, we just have this fact. And based on that fact, we can move forward with a solution. Now, we also know that the sample standard deviation is equal to the population standard deviation over the square root of n. So that's good. We've got 7.2 for our standard deviation. We have 36 for n, so we can calculate out a sample standard deviation in this case. And so we have 1.2. And we now know that, of course, x bar is normally distributed. So B is asking us to show that approximately 95% of all samples of 36 new mobile homes have the property that the interval from x bar minus 2.4 to x bar minus or plus 2.4 contains mu. So what they're asking us to do here is kind of to apply property 2 of the empirical rule, which implies that for a normally distributed variable, about 95% of all possible observations lie within 2 standard deviations to either side of the mean. And so we just can apply that rule. If this holds true, then X bar plus or minus 2 times the standard deviation will be the range that we're looking for. So if, for example, X bar is equal to 63.28, and I'm just telling you that, you didn't calculate that from anywhere, find the 95% confidence interval or the bookends. So what you have to do is take X bar minus 2.4, and where did I get the 2.4? It is 2 times our standard deviation that we had of 1.2. So 2 times 1.2 is equal to 2.4. So we'll take X bar minus 2.4 and then X bar plus 2.4. And then what we can say is that we can be 95% confident that mu, or our population mean, is going to lie in between 60,880, which is the 60.88 here, and 65,680, which is this one down here. And so we can say equivalently, approximately 95% of all samples of 36 new mobile homes have the property that the interval from X bar plus or minus 2.4 contains mu. And where might you use this type of confidence interval or this information? Well, you can apply it to medical, healthcare really, really, really well. So patients, environments, situations, they're all variable. So you can think about the weight and length of babies born, or maybe it's the weight and length of babies born with a certain condition. Medication amounts based on patient sizes. It's very important in clinical trials and when we're looking at the effectiveness of treatments. So for example, assessing the impact of a new drug or procedure, such as determining the mean difference in recovery time or calculating number needed to treat to show the range of benefits. It's also used quite a bit in epidemiology and public health. This is when we estimate prevalence, incidence, risk, or mortality rates, especially for small numbers where uncertainty can be very high. These are the definitions for our confidence interval estimates. A confidence interval, or CI, is an interval of numbers obtained from a point estimate of a parameter. Confidence level is the confidence we have that the parameter lies in the confidence interval, or that the confidence interval contains that parameter. And then we've got confidence interval estimate, the confidence level and confidence interval together. So a confidence interval estimate for a parameter basically provides a range of numbers along with a percentage confidence that the parameter will lie within that range. I want to talk about the importance of interpreting a confidence interval correctly. And so we're going to do that by looking at this example. So in this example here, a computer was used to simulate 25 samples of 36 new mobile home prices each. For the simulation, there was an assumption that the mean was 65,000 and that the standard deviation was 7.2 thousand. In reality, we don't really know what the mean is, the population mean, but we're just going to assume a value so that we can illustrate this point. For each of the 25 samples, there were 3 things that were done. The sample mean price was computed, and that's X bar in the chart. And we've got the 95% confidence interval using the equation for the confidence interval. And you can see that on the chart as well. It says 95% confidence interval, and it's giving you a range from a lower number to a higher number. And then finally, they're asked the question, is the population mean of 65,000 within that confidence interval that was calculated? And so if you look at the dot plot that we have, you can see that it centers on our mean of 65,000, and the dot the horizontal lines represent the corresponding 95% confidence interval. And so what you'll see is that the population mean lies in the confidence interval only when the horizontal line crosses over with the dashed line. So there is a 95% confidence interval, and we've got 24 of the 25 samples that actually do fall within that confidence interval. So you can see that there is only one that does not fall within it. And this leads us to our next topic of discussion, which is the margin of error, which indicates how accurate our guess will be. And I already said this, but the margin of error indicates how accurate our guess is as an estimate for the value of the unknown parameter. And this expression will be the form of most of the confidence intervals that we are going to look at in statistics. One thing I really want you guys to take away from this is that we can express the endpoints of the confidence interval as our point estimate plus or minus the margin of error. And of course, the margin of error is always going to be half the length of the confidence interval, or equivalently, the length of the confidence interval is twice the margin of error. So you can use that to help you calculate things should you need it. So most of the things that we looked at prior to this part here is really just building up to learning about how to do these confidence intervals. So now we're going to do a step-by-step procedure to get a confidence interval for a population mean when the standard deviation is known. And in doing so, we assume that the variable under consideration is normally distributed. And we're going to have a little conversation about a thing called assumptions. Before we get to that procedure, though, let's talk about the basis of the confidence interval procedure. So if x is a normally distributed variable with a mean mu and a standard deviation sigma, then for samples of size n, the variable is also normally distributed and has a mean mu and a standard deviation of sigma divided by the square root of n. Property 2 of the empirical rule says that 95% of all samples of size n have means within 2 standard deviations of mu. And these are just pieces of information that we need so that we can move forward with calculating our confidence interval. And this leads us to the one mean Z interval procedure, or you can just call it the Z interval procedure if you don't get confused about the mean part. So with the one mean Z interval procedure, the whole purpose of it is to find a confidence interval for a population mean of mu. And this is the equation for it here. It is x bar, and you'll see it on your formula card as plus or minus, which means you have to do it twice, once for subtracting and once for adding. So it's x bar minus plus or minus z alpha divided by 2 multiplied by the standard deviation over the square root of n. And this is the confidence interval for mu. And we're going to walk you through how to do this, but it's very important that you also get your formula card out and take a look at this and make sure that you know where it is. This is the procedure for the one mean Z interval. So again, the purpose is to find a confidence interval for a population mean mu. And it has a thing called assumptions here. And this is something that's going to come up over and over and over again. And in fact, a lot of these assumptions are written on your formula card. So what is an assumption? The name is kind of not great. It's saying it's an assumption, so you would say it is assuming all of these things about your data set. The way I like to look at it is a checklist. If you've met all of the things on this checklist, then you can run this particular test. So let's look at them. The first one is it's a simple random sample. How can you look for that in a question? You can't really. They'll just tell you it's a simple random sample. There's really no other way that you can verify that. It is a normal population or a large sample. So how can you check to see if you have a normal population? You can do a QQ plot, or you can do a Shapiro-Wilk, or you can do both of them to make sure that the data is indeed normal, or you have a large sample size. And of course, we'll talk about what that means coming up. And in this case, we need to know our standard deviation. If we don't know the standard deviation, then we can't actually run this test. So you're going to see this. There's going to be assumptions about all of your different tests, and you need to consider them like a checklist. If you don't have these things, then you cannot run the actual test, okay? And that's why we spend a lot of time talking about descriptive statistics so that you know exactly what you need to do to look for the things on that checklist. Okay, so the first thing that we have to do is we have to find our confidence level using our table 2. So we always have a confidence level of 1 minus alpha. By saying that the confidence interval is exact, we mean the true confidence level equals 1 minus alpha. So in this case, Well, you know what? I'll hold off on that and we'll just do the example together. So just know that we will have an alpha and our confidence level will be 1 minus alpha. And then what we'll do is use that information to find our Z alpha divided by 2, which then we can pop into this part of our equation here. Now, then we can interpret the confidence interval from there. So this is the procedure, but we've got to put it into play. So do you remember when the assumptions were saying it has to be a normal distribution or it has to have a big sample size? What exactly does a big sample size look like? So there's a key fact when to use the one mean Z interval procedure. For small sample sizes, they're saying less than 15, the Z interval procedure should be used only when the variable is normal. For samples of a moderate size, so they're saying between 15 and 30, the Z interval procedure can be used unless the data contain a lot of outliers or the variable is really, really far from being normally distributed. And if you've got samples 30 or more, then you can use the Z interval procedure without any restrictions. Even if there are outliers present, you can still do it, go forward with a really large sample size, because what it is that it is robust to moderate violations of normality. So that's a kind of a term you'll hear in statistics. It's robust. If outliers are present, but their removal is justified and results in a data set for which the Z interval procedure is appropriate, the procedure then can be used. So size does matter. And this is what I was talking about before with the assumptions or your checklist. It's the fundamental principle of data analysis. Before performing a statistical inference procedure, examine the sample data. If any of the conditions required for using the procedure appear to be violated, do not apply the procedure. Instead, use a different, more appropriate procedure if one exists. So often you'll have that it has to be a simple random sample. And that's just the process of making sure that they obtained the data in a correct and random way and that the data is normal. Now, what happens if the data is not normal? Then what can we do? Well, we have some options. So we can use a thing called non-parametric statistics. So inferential statistics is also a type of parametric statistics. And if you have a non-normal distribution, then you switch over and you use a non-parametric statistic, which you don't really learn too much about in this course itself. Just a few little pieces of it. And the final thing is that you have to make sure that you have all of the pieces you need to actually run the test. So you can't run a one mean Z interval procedure if you don't actually have the standard deviation, for example, but there are alternative tests that you can run where you don't need the standard deviation. So it's basically just always look at your data ahead of time to make sure that you've got that checklist of items. So let's revisit step 1 of the procedure where we need to find Z alpha divided by 2. So we'll use our standard normal table or table 2 to get these values. Anytime you see Z or a Z in there, it's going to be table 2. Now, when I say that it is 1 minus alpha, what you'll have is you'll have a confidence interval or a confidence level, sorry, that has been specified. So say a question asks you to find some sort of a confidence interval with a 90% confidence level or 95 or 99. What that means is it means 1 minus alpha. And so what you do, and I'm just going to make that little alpha symbol. So what you do is you go 1 minus 0.90, and that will give you your alpha level of 0.10. And you do the same thing. So 1 minus 0.95 is 0.05. 1 minus 0.99 is equal to 0.01. The next part of that then is to use your table 2 to actually find the corresponding Z alpha divided by 2. So in this example, let's work with our 95% because this is the most common one. So 1 minus 0.95 is equal to 0.05. Z alpha divided by 2 then, so you take 0.05 and you divide it by 2. What you would end up with then is Z 0.025. So that will be equal to 0.025. 0.25. So you can try that out. All it is 1 minus 0.95 is equal to 0.05 divided by 2, and that gives you 0.025. Now, the next part of it, it's weird, but just follow me with it and just kind of go with it. Because even if you don't fully understand why you do it, you just know you need to do it. The next part that you do is you take 1 minus 0.025 and you get a number. That number is the number you look at in the body of the table to then find your Z values. So I'll show you more examples of that, but I just wanted to give you this chart here and just talk about what 1 minus alpha means. Okay, let's do an example, and this is the perfect time for you to grab out table 2 because you're going to need it. So find a 95% confidence interval for the mean age mu of all people working in emergency rooms. Assume the population standard deviation of the ages is 12.1 years, and the mean was calculated from 50 randomly selected people and is 41.4 years of age. So right from the get-go, you see a question like this, and if you start pulling out the pieces of information and writing it down, it almost tells you exactly what you can do with like which test you can run. So 95% confidence interval, standard deviation, population standard deviation, so sigma 12.1, the mean is 41.4, and we've got an n equaling 50. Okay, so find a 95% confidence interval. So we want the 95% confidence interval. Our first step then is to find our alpha, and we want 95. So remember, it's 1 minus 0.95, which is equal to 0.05. The next part then is Z alpha divided by 2. So Z 0.05 divided by 2 is equal to 0.025. Now, where did I get the 0.05 from? I got it from here, 1 minus alpha, 0.05. Why do I divide it by 2? Because the equation is Z alpha divided by 2. Then what I do is I take 1 minus 0.025, and in the body of the table, so this is where you pull out your table 2 and look in the body of your table for 0.975, and then match that up to the column on the very left hand side and the row along the top, and you get the number 1.96. That's this number right here. So everything else you already have X bar. Now you have this, you've got a standard deviation, and you've got n. So you'll run the equation twice, once to subtract and once to add, so that you get the range. So this is where you'll want to try it out. 41.4 years, the mean, minus 1.96, which was our Z, times 12.1 divided by the square root of 50, and then you do it again, but you're adding it. And then in this way, we can be 95% confident that the mean age of people working in emergency rooms is somewhere between 38.0 years and 44.8 years. Okay, so now that we've done an example, let's revisit the margin of error. So the margin of error, of course, is an estimate of a population mean, and it will help indicate the accuracy with which a sample mean estimates the unknown population mean. And so you can see in this picture below that the blue line actually represents the confidence interval itself. So you can see right there, this part here, this blue line here, that represents the confidence interval. Now remember, the margin of error equals half the length of the confidence interval, or the length of the confidence interval equals twice the margin of error. So we can use either the length of the confidence interval or the margin of error to measure the accuracy of a point estimate all the time. And one thing I didn't mention in the last slide is that the margin of error is often denoted, or usually denoted, with a capital E for error. And so, of course, then we can use this equation transposed to actually calculate our error. So in this example here, a sample of 62 gives a mean annual income of $3,313. We have a standard deviation of 862. Find the margin of error in estimating mu at the 99% level of confidence. So again, just always start by writing out what you know. You already know the standard deviation is 862. Our alpha is 1 minus 0.99 because it's at the 99% level. And of course, then we can find Z alpha divided by 2 by taking our 0.01, dividing it by 2, and then we get 0.05. 1 minus 0.005 is equal to 0.995 in the body of the table. And in this particular situation, what you'll find is that there are two z-scores that are equal, and so then you would take the average of them. So you need to pull out your table 2, make sure that you can do this. Try to find 0.995 in the body of your table. And they've given us x bar and they've given us 62. So we can calculate a margin of error here by putting in 2.575 times 862 over the square root of 62. Now, I'm not going to put the answer up on here. I want you guys to try this yourself, but you should be able to get about 281.89 as your answer. And let's do just another quick example here. And this is a really easy one. I put them on assessments quite a bit because they're easy for you guys and easy to mark. So a confidence interval for a population mean mu has a length of 122.1. Find the margin of error. It's really, really easy stuff. It is half the length. So 122.1 divided by 2, the margin of error is equal to 61.05. Really easy peasy. And if they gave you the margin of error, you could simply multiply by 2, and then you would get the confidence interval. And a key fact for you guys, confidence and accuracy. For a fixed sample size, decreasing the confidence level decreases the margin of error and hence improves the accuracy of the confidence interval estimate. So basically, increase the sample size if you want to decrease the margin of error. One thing that I really like about math is that you can transpose equations and you can find other information that you need based on some of the information you already have. So in this example here, you can actually calculate a sample size, which is so handy if you're doing research and you want to make sure that you're not doing more than you need to or getting too few numbers. So sample size for estimating mu. The sample size required for a 1 minus alpha level of confidence interval for mu with a specified margin of error E is given by this formula. So the problem with this formula is that we do need to have some sort of a margin of error, but we can calculate N with Z alpha divided by 2 multiplied by our standard deviation over the error all squared. And let's do an example of that. Determine the sample size needed to be 95% confident that mu is within 0.5 of the estimate. So in this case, our E, our margin of error, is going to be 0.5. And we've got an X bar of 38.8, and we have a sigma of 12.1. So what do we know? Well, we have a sigma, we have an X bar, and we have E. We don't actually need the X bar though, so that's kind of handy. So the confidence level is 0.95, and that means our alpha then is 0.05, because remember, 1 minus 0.95 is equal to 0.05. Then we take Z alpha divided by 2. 0.05 divided by 2 is 0.025. What's not shown on here is 1 minus 0.025 gives you a number to look up in the body of the table to get 1.96. But you guys have that chart from before as well. Often what you're going to see is it's either going to be 90, 95, or 99%. So you often start to memorize these Z alphas. So let's pop all of the numbers in here, and you should try this in your calculator. I'm going to give you guys assessment questions like this, like a real easy one where I've given you all the pieces and you really just need to pop it in and make sure that you know how your calculator works. So in this question, what you end up getting is 2,249.79 as a sample size. So as a researcher, you're just going to say, okay, well, I'll do 200 or 2,250. And then you've got the exact sample size you need to be within a certain margin of error. Okay, another example. Find a 95% confidence interval for mu if a sample of the size determined in the last example has a mean of 38.8. So what do we know? They're asking us to do a confidence interval. We have an X bar, we have a Z alpha divided by 2, we have a standard deviation, and we have a sample size now. And you can see that they did the same thing that I would have done, which is just round up. And so again, it's just transposing the equation back and forth so that we can estimate a sample size, and now we can go back and we can estimate a confidence interval. And another example here, a confidence interval for a population mean has a margin of error of 7.4. Determine the length of the confidence interval. And remember, the margin of error is equal to half the length of the confidence interval, so you simply just have to multiply by 2. Okay, we'll wrap this up with some key facts. So x bar plus or minus e can also be used to compute the confidence interval, but it will give you a slightly more conservative estimate. Sometimes we don't have the standard deviation, the population standard deviation, sigma. So if that case happens, what we'll do is we take a large sample and use the sample standard deviation S in place. And that will be kind of the next topic we talk about. A high confidence level and a small margin of error is obviously ideal. This can be accomplished, but we need to have a large sample size, and that's often not possible. But the formula for finding the sample size is something that now you know, and so we can use that to help us. Ideally, we want to have high confidence and a small margin of error, and of course, we need to take into consideration the sample size and the available resources you have as a researcher, and this could be things like money or personnel, and these often restrict some of our situations in which we want to get some data analysis.